So now you know that neural nets have some pretty cool applications, but how they work? That's what I'll explain in this video. Let's take a look at a model of a neural net. Wow, that definitely looks scary. You might think. The first part of a neural net is the input. These are the first circles on the neural net. Here you can plug in the raw data, and our model 2 and 3 could be the inputs. Let's show this on our neural net. That part is relatively straightforward. All of these lines represent weights. Weights are simply numbers that you multiply by the input to change it. Weights are progressively adjusted and fine-tuned, so when the inputs are multiplied by the final weights, the expected outputs are obtained. But how do we find the best weights? Well, this is a key aspect of neural networks that I will be explaining later in this video. To start with, you initialize the weights to random values, and I will show you how exactly we adjust them later on. If you missed my previous video, you may be wondering, if I already have inputs and the corresponding outputs, why do I care about finding the relationship between inputs and outputs? The answer is that it allows you to make predictions of an output which you don't know the value of when a new input is presented to you, even when the relationship between input and output are complex and unknown. Another important part of a neural net is the bias. It shifts the entire output. It's really just another way to adjust or fine-tune the output. It makes sense why you would need weights in a neural net, but why exactly do you need a bias? To demonstrate why we need a bias in our neural net, I will be using a very simple function, that of a straight line. First, let us define what a function in general is. A function is simply a set of inputs and outputs, in which each input has one output. In other words, it is a way to describe the relationship between inputs and outputs, where you can plug in an input and get the corresponding output. What is the function of a straight line? Y equals mx plus b, where x is the input, m is the slope of the line, b is the y-intercept, or the value of y when the line crosses the y-axis, and y is the output. This is because in a neural net, you multiply the weights by the input, or in other words, x. And in the function of a straight line, you multiply m by the input, or x. And in a neural net, you also add a bias to the sum of the weights multiplied by the inputs. As I said before, we do this in this equation with a b. Let's begin by plotting the line without a b, or in the case of a neural network, without a bias. If we were to plug in 2 for the slope, our equation would be y equals 2x. If we were to plot it, it would look like so. Now, let's change the slope to 4, making the equation y equals 4x, and making the graph look like so. If you notice, the only thing that changes when I change the slope is how steep the line is. By only changing the slope, I will never be able to make a line like this. In a neural net, you find the best fitting relationship between the input and the output, and it just might be the case that the best fitting relationship between the input and the output is this line. So how can we create this line? The answer is that we can simply add a y-intercept of 3, or in the case of a neural net, we can add a bias. This will shift our line up, making it cross the y-intercept at 3, and change the equation to y equals 4x plus 3. Keep in mind that the relationship between the input and the output in a real neural net will most likely never be a perfectly straight line, but nevertheless, the bias will serve the purpose of shifting the input or output relationship that would be much more difficult to achieve using only the weights. Programmers initiate the bias value to 1 and then multiply that value by a weight, which will be initiated to a random value. We will also adjust the value of the bias weight later on to try and find the best fit between the inputs and outputs. We have now multiplied our inputs by our weights and multiplied the bias by its weights. Before we move on to the next step, let's define some vocabulary. Each circle that you see here is known as a neuron. This is the input layer, and these are the input neurons. Their job is simply to hold the input. The lines are known as synapses, and here we multiply the inputs by their weights and the bias by its weight. Here we have another layer of neurons. This layer is known as the hidden layer. In a big neural net, you will have many of these. But for our model, we will only have one hidden layer. In the hidden layer, the different neurons allow you to fine-tune the relationship between inputs and outputs. The number of neurons in a neural net is fixed, and so it is generally up to the programmer to decide how many he or she might need for the specific application of a neural net. For our simple model, we won't need many neurons in this layer. Next, you have more synapses, and finally, you have the output layer and its output neurons. Their job is to hold the output. The next step is simply summing up every value coming into each of the hidden layer neurons. This is quite simple. Now, let us simply define some equations that express everything that I've just talked about. Our neural network for this video will have 2 input neurons, 1 hidden layer with 4 neurons in it, and 1 output neuron. We'll call x1 the input from our first input neuron, and x2 the input from the second neuron. We will also call w1 the first weight, w2 the second, w3 the third, w4 the fourth, w5 the fifth, w6 the sixth, w7 the seventh, and w8 the eighth. In addition, we will call b1 the bias for our hidden layer neurons, and bw1 the bias weight for the first neuron in the hidden layer, bw2 the bias weight for the second, bw3 for the third, and bw4 for the fourth. Finally, we will call the sum of the values coming into the first neuron, Act 1, into the second neuron, Act 2, into the third neuron, Act 3, and into the fourth neuron, Act 4. First, we will define Act 1 as Act 1 equals x1 times w plus x2 times w5 plus b1 times bw1. This is because we multiply the first input by this weight, w1, we multiply the second input by this weight, w5, multiply the bias by its weight, bw1, and then we sum these 3 values because they come into the first hidden layer neuron. Similarly, we can define Act 2 as Act 2 equals x1 times w2 plus x2 times w6 plus b1 times bw2. You guessed it, the equation for Act 3 is Act 3 equals x1 times w3 plus x2 times w7 plus b1 times bw3. Finally, the equation for Act 4 is Act 4 equals x1 times w4 plus x2 times w8 plus b1 times bw4. Now we will apply an activation function. We do this to every neuron in the hidden layer and in the output. The role of an activation function is to make the relationship between the input and the output nonlinear. If we didn't apply an activation function, the relationship between the input and the output would be linear. This is an example of the graph of a linear function. In many real-world data sets, the relationship between the input and the output is very, very complex, and therefore not linear, or in other words, nonlinear. This is exactly what the activation function does. It spices up the neural net, making it capable of finding a much more complex relationship between the input and the output. For our activation function, we will be using a sigmoid. This is not necessarily the best or most efficient activation function in all cases. However, in general, it does the job. Okay, let's get back to our network. As I have previously said, you apply an activation function to both the hidden layer and the output layer. And so we will also apply the sigmoid activation function to both the hidden layer and the output layer. The graph of a sigmoid function has a nice S shape, and it nicely places the input values between 0 and 1. This has the benefit of compressing any possible input into a well-defined range. I'm going to go over some math. The formula for sigmoid is 1 over 1 plus e to the negative x, where e is just a constant. This will be important when we implement this later on in our Python code. Basically, we will input our value from before when we summed everything up as x in the sigmoid formula. This means that we will input Act 1, Act 2, Act 3, and Act 4. And I will call the outputted value SAct1, SAct2, SAct3, and SAct4, respectively. So SAct1 is the sigmoid of Act 1, SAct2 is the sigmoid of Act 2, SAct3 is the sigmoid of Act 3, and SAct4 is the sigmoid of Act 4, where we just replace the value of a certain act with the x in our formula. Now that we have done this, we will use the values coming out from the sigmoid function from each hidden layer neuron as the inputs for the output neuron after we multiply it by its corresponding weight. So we will obviously need to multiply these values coming out from the sigmoid function by a weight that, you guessed it, will be initiated to a random value. Next, we will sum up every value coming in to this last output neuron. We can call this new function ActA and define it as ActA equals SAct1 times WOut1 plus SAct2 times WOut2 plus SAct3 times WOut3 plus SAct4 times WOut4 plus Bout times WBout. Finally, we will apply the sigmoid function to this new summed up value, as we have done for the hidden layer neurons. We can call this output from our neural net y hat, and it is the estimated value of the real output y that our neural network has predicted. Now we have a neural net, right? Well, yes, we do. However, what our program is currently doing is multiplying some input values by random numbers, so it makes sense why it couldn't be used for anything just yet. The real magic happens when we adjust the value of the weights to make the neural net to make accurate predictions of the outputs given an input. That's it for this video. If you want to ask me a question, or just tell me in the community about something that you think is relevant, leave a comment in the comment section down below. If you enjoyed the video and want to see more, please like, subscribe, and hit the notification icon.